Hey guys, welcome to the lecture series of Elementary Classical Mechanics, where we will embark our journey from basic to advanced physics. This is part 2 of lecture 4, where we learn about instantaneous acceleration. Contents. We are going to learn about average acceleration, instantaneous acceleration, commonly called as acceleration, and problem and its analysis. So let's get started. Just like we have started with average velocity in the previous lecture number 2, we first define average acceleration. Average acceleration is defined as rate of change of velocity. What that sentence mean by that? When the velocity is varied or changed with time, that quantity will be acceleration in general. The mathematical form of average acceleration is delta v upon delta t, where delta v is change in final and initial velocity. Now, only the matter of difference in average acceleration and instantaneous acceleration. The difference between the average acceleration and instantaneous acceleration is similar like average velocity and instantaneous velocity. Average acceleration is defined as delta v upon delta t, which implies that for a given initial and final velocity and their time at that initial and final moment, just like average velocity, unlike the change in position. This also means that average acceleration will not be able to tell the acceleration in between any time for the interval of delta t or in between change in time. But this con is overcome by the limit. When the limit of delta t tends to or approaches to 0, then we get the derivative form of acceleration. For this very small delta t, this equation called as instantaneous acceleration or just acceleration. Acceleration is a vector quantity which has both magnitude and direction. Its unit is meter per second squared because if you think about it, velocity has unit meter per second and time is in second. Therefore, we get unit of acceleration as meter per second squared. When we substitute the derivative form of velocity, you will get as double derivative as d squared x of dt squared. There is always a difficulty in understanding that what signs actually do. So some people might say it gives the direction. Yes, that is true. The sign in front of the quantity will give us direction. But it does more than that. For example, when we will get negative acceleration, that is initial velocity is greater than the final velocity. For example, a car going with a speed of 30 meter per second then stopped after 3 seconds. Then initial velocity is 30 but finally 0. Therefore, the speed is decreased. This decrease in speed results in decrease in acceleration, which is also called as deceleration. Now the main point. For this you might get little confused, but you should brace yourself to think little hard and listen to me very carefully. When you get velocity and acceleration of the object of same sign, then speed of the body increases. And when you get the velocity and acceleration of the object of different sign, then the speed of the body decreases. Let me clarify the above statement by an example. Consider a car that has the initial velocity as negative of 20 meter per second, then comes to a stop in 5 seconds. After substitution of respective values and calculating, we get the acceleration as positive of 4 meter per second squared. But still the car has decreased its speed. The opposite in sign of acceleration and velocity will tell us that the body is decreasing its speed. This is the proper way of interpreting the sign of these quantities. There is a man with a skateboard who has the position x at a time t according to this equation below. X equals to 5 plus 40 minus t squared. Our aim is to find the following. A. Its velocity and acceleration. B. The time at which the velocity and acceleration is 0. C. The velocity and acceleration of skateboard at time t equals to 0. Please pause the video and try it out yourself. For velocity, we find the derivative of x with respect to time t. Then we write as dx by dt equals to d by dt of 5 plus 4t minus t squared. For this, we use the formula of derivative of x raised to n. So, using the formula and distributive property, we get derivative of position of x with respect to time as 4 minus 2t. This is velocity. Now the acceleration. The acceleration will be derivative of velocity with respect to time. So we get dv by dt equals to d by dt of 4 minus 2t. Again, applying the distributive and derivative formula with respect to time, we get acceleration as negative of 2 meter per second squared. Now we have velocity as 4 minus 2t and acceleration as negative of 2 meter per second squared. Part B. The time at which the velocity and acceleration is 0. So when velocity is 0, we should take v equals to 0. Then we get 4 minus 2t equals to 0. Then rearranging, we get t equals to 2 seconds. The acceleration cannot be 0, rather a form of deceleration. We have as negative of 2 meter per second squared. There is no t time variable in this equation, therefore acceleration is constant. For part C, we need to find the velocity and acceleration at time t equals to 0. So by substituting t equals to 0, we get velocity as 4 meter per second and still acceleration will remain the same. Now let us plot the analysis of this problem. Here we have velocity as 4 minus 2t and acceleration as negative of 2 meter per second squared, which we have derived from the behavior of skateboard in the form of equation, which was x equals to 5 plus 4t minus t squared. Let us see at what position the skateboard for time t. So at first we start the time from 0. When time t equals to 0, after substituting, we get the skateboard was at 5 meter. The time at which the skateboard stop is at 2 seconds. So as we have predicted before, now at time t equals to 2 seconds, when the skateboard stops, he will be at, by substituting t equals to 2, we get 9 meters. Now if we fill the numbers in between 0 and 2 seconds and substitute in the equation, then plotting for the position versus time, you will get such behavior. At time t equals to 0, the skateboard was at 5 meters and at t equals to 2 seconds, he stopped at 9 meters. See how the line is in increasing direction, which tells us that the person on skateboard is moving forward. You can find the velocity just from the graph by finding its slope. Now let us check what happens when we plot velocity versus time. Initially skateboard was at speed of 4 meter per second. Then at time t equals to 2 seconds he stops, which we have predicted from the problem. This line on a graph is decreasing the trend. This shows that with time evolution velocity is decreasing, and just like before you can take its slope and can find its acceleration. For graph of this acceleration, the acceleration we found out that is constant throughout the journey of skateboard. So we get the constant trend like this for negative of 2 meter per second squared. This form of reading is graphical reading and it is very useful for understanding the motion of the body. I will soon take some problems based on these topics in my new playlist. If you have any questions, doubts or any defects in my teaching style, use the comment box. For discussion of the topics and problems, we can do that on Facebook inbox or in the group Physics Discussion via Phi Shastra. You can support me on Facebook and Instagram by following @Phi Shastra. Link in the description below. Please subscribe my channel. Your gracious subscribe will encourage me to work harder and more better. Till then, stay tuned.